Okay, hello, welcome back. Okay, let me just make sure the stream is working properly. Everything is okay. Okay, it seems like everything is okay, so let us begin. So for this particular one, we will only be doing the last, the four questions which are different from the junior section, because the junior section we have covered in the junior live stream. So if you have not checked out the junior live stream, you can go and check it out. So anyway, we'll only be doing four questions here, so probably just maybe 20 minutes and then we'll be done. Actually, maybe not 20, maybe it's closer to 30. Okay, let's do this question number 8. It says that a move is defined as the three numbers in a row or a column, right? Very importantly, actually, or column, either adding or subtracting k, where k is a positive integer. For example, here is one move for the middle row where k equals to 1. Right, we add 1 to the middle row. Wait, sorry. Not add 1 to the middle row. Sorry. We take the middle row, we go and increase the 3 and the 2 by 1. So the 2 plus 1, sorry, the 2 and the 1 by 1. So 2 plus 1, 1 plus 1 by, take 9 and minus 1, I can get 8. Okay, so this is what happens here. Now, is it possible to turn all nine numbers in the table below in the same number if you just show operations clearly and if not give a reason to support your answer? So whenever these kind of questions are being asked, the answer is going to be 95% of the time it's going to be a no, because it's, if you actually try to do a way to turn all nine numbers the same number, it will be very, very tedious, right? So the answer should be a no. But the question, the reason becomes, or rather the thing becomes, how can we show that this thing here will become a no, right? How does that work? The idea here is that we can look at, for example, a group of three numbers. Okay? We can look at a group of three numbers. So what we can do is that we can look at this group of, okay, let me draw an empty 3 by 3 grid. Let's take a look at this group of three numbers here. The one in green color, right? Then I'll call another one, I'll call the one in black color, and I'll call the one in red color. Okay. So let's take a look at this group of three numbers, or rather this way of arranging a 3 by 3 table. Now, here's the thing. Every operation will do the same thing to the sum of the green color, sum of the black color, and sum of the red color. Right. So every operation will change the parity of the sum of green, sum of red, and then sum of black. Okay. So what does it mean? For example, if you take a look at the starting point, right? The black color contains this tree, right? Now you change the middle row, you change the middle row by plus 1. What happens to the sum of these three squares? The sum of these three squares increases by 1, right? Let's say you're looking at the one in green color. The one in green color is here, here, and here. By doing this operation to 9 minus 1 from 9, you have changed the green color by minus 1. So if it's previously even, it'll be now odd. If it's previously odd, it'll be now even. Okay, so that will be the case here. Now, oh, wait, where's the question again? Sorry. Okay, then if you do it for the one in, for the one that's here, um, here, here, and here, right? Then the same thing will happen. Same thing will happen where, if you change the plus 1 in the one in the red color, you change the parity of the one in red color as well. Okay. So every operation will change the parity of the sum of green, sum of red, and sum of black. Now, actually, I just realized a bit of a mistake I made. I want to recolor these three things. Okay. I'm going to recolor them. The reason is because of the odd and evenness of the numbers. If you take a look at the starting odd and evenness of the numbers, you'll notice that only the three twos are even, right? So what I'll do is that I'll color it in this way instead. I'll color these two with red and this one with red. I'll color these three in green. I'll color the remaining three in black. Right. So now you can see at the start, what happens? At the start, the sum of green is even, right? Because 2 plus 9 plus 1 is even. But the sum of red and sum of black are both odd. Okay? Hence, at the end, it is not possible for the sum of green to have the same uh, parity as the sum of red and sum of black. And then you're done. Finish. That's the entire proof. Okay. So the answer is no, because of parity, because of the even and oddness of your number. Right, you notice that the original three squares in green color, they add up to even, but the original three squares in red color and also in black color, they add up to an odd number. So therefore, at the end, it's not possible for the sum of the green to have the same parity as the sum of red and sum of black. And that's the answer. Okay. So this is quite a high level kind of idea. You don't usually see this in primary school math Olympiad competitions. It's usually a secondary school Olympiad competitions kind of idea, but it's quite creative. Okay, question number 9. Triangle ABC is an isosceles triangle. The perpendicular height from A onto BC is half the length of BC. Find all values of angle BAC. There's basically only two scenarios. Scenario 1, case 1, right, is when AB equals to AC. Then the perpendicular height from A onto BC is half the length of BC itself. So how does it look like? So that means if I want to draw the diagram more accurately, this height needs to be even smaller, right? So it needs to be half the length of BC. So then if you go and adjust the height according to this, then the diagram will actually look closer to this diagram here, right? Where the height A to BC is half the length of BC. Now, what does it mean? If AB equals AC, then by symmetry, these two things are equal, right? But since the height is half the length of BC, it means that this is also equal. So therefore, in this first scenario here, we can have the angle A equals to 90 degrees. Okay, case 2 will be the other two cases, which is that BC equals to one of the other sides. Now, it doesn't really matter whether BC is equals to AB or AC because it is the same as symmetry. Okay, so let's say that this is BC, right? Let's say this is BC, yeah? For BC to be the same as one of the other side have to be the same length as BC, so something like that. And then in that case, your perpendicular from A is going to be half of BC, yeah? So this is what it looks like. Now, if it's half of BC, then let's say this is 1 unit, then BC will be 2 units. Then in that case, AC will be 2 units. And from AC being 2 units and the height being 1 unit, you can see that this is a 30, 60, 90 triangle. Okay? And from this being a 30, 60, 90 triangle, and the fact that these two are equal, you can see that angle A will be 180 degrees minus 30 degrees divided by 2. The answer is 75. So the answer for this question is either 75 or 90. Okay. Wait a minute. Let me just wait. There's one case I'm not considering. Wait. I just realized there's one case I have yet to consider. Sorry. There's one case I have yet to consider. Wait. Case 2, you need to be a bit careful. This is wrong. This is wrong. Case 2, you need to be a little bit careful because of the fact that there could be a case where it is obtuse, I think. Yeah, there could be a case where it is obtuse. So in in another scenario, so actually case 2 is not the only one. Okay, so maybe I just bring this case go to the left. Okay. In another scenario, you could also have the same situation but with the angle being obtuse. But you don't need the triangle to be an acute angled triangle. So you can also have, for example, this is your BC. Uh, this is your BC here. Then you can also have, let me shrink it a little bit. You can also have a situation where you have this length is equal, right? And then the height itself is this one here. So in why I forgot about this case is because I thought that maybe the height will also have to lie within the triangle, right? But the answer is not necessarily. So this is your A, this is your triangle ABC, right? You can see it's isosceles. BC is equals to AC, and then the height will be half of the length of BC. Yeah? So in that case, we can do something similar. In this case, this is 1 unit, this will also be 2 unit, this will also be 2 unit. Then this will be a 30 degree, right? 30 degree here. So in that case, because it's isosceles, both of these angles will be 15 degrees. So actually, that is also a possibility, right? So actually, the answer for this question is supposed to be 15 degrees, or 75 degrees, or 90 degrees. Yeah. Sorry about that. Okay. Question number 10. Question number 10 tells you that AABCD is a 5-digit square number where ABCD can be from any digits from 0 to 9. But A and D must both be bigger than 0. Now they tell you that DCBAA is also a perfect square number, least all possible values of ABCD. How to begin? Right, seems like there's no way to begin. Well, you begin from here. So the question is, can square numbers can square numbers end in can squares end in 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6, 7, 7, 8, 8, or 9, 9. But we already know that A cannot be 0, so we don't have to consider that. Firstly, square numbers cannot end in 2, 3, 7, and 8. So immediately these are not possible. What else can we remove? We can remove 55. Because if it's divisible by 5, it's also divisible by 25. So it's either going to be ending in 25 or 75. This is gone. What else is possible? 11 is not possible because 11 is divided by 4 remainder 3. And square numbers only divide by 4 remainder 0 or 1. So 11 is also gone. In the same way, 66 is gone because 66 divided by 4 remainder 2. So square numbers can only end in, wait, 99 is also gone because 99 divided by 4 is remainder 3. For the exact same reason, 99 is gone as well. So from here we can know, okay, the only possible choice of A must be 4. Right? This is the only possible outcome. Because it's either impossible to end in the rest or the others, they divide by 4 have a remainder that's not 0 or 1. Yeah. So it's only possible end in 44. That means we know that A must be 4. Right? And if A is 4, then things are a little bit easier because I know that this is 44,000 BCD. Then we can try to use some estimation to go and calculate out what this is equals to, right? Isn't it? So we know that 210 squared is equals to 44100. Right, that's 210 squared. So this is a possibility. There's nothing that's smaller than this. But this is obviously impossible because D is 0, right? What about, let's say, 211 squared? 211 squared is going to be 4110 plus 210 plus 211. So it's 410 plus 421. So it's 44521. Yeah, 44521. And then what about 212 squared? Is 44521 plus 211 plus 212. So that's 423. So it's 449 449 223 plus this is 44. So immediately we know this is possible, right? 44944 is definitely our answer already. The only thing left to check is to check whether 44521 is within our answer as well. All right, so let's see whether this guy is within our answer. So 12544, is this a square number? Well, let's try. If I have 110 squared, that's 12100. If I have 112 squared, what's that equals to? 112 squared is going to be 110 plus 2 squared. So that's 110 squared plus 2 times 2 times 110 plus 4. So this is 12100 plus 440 plus 4 is 12544. So yes, 12544 is also a square number. So that's it. We're done. The answers are uh, 44521 and 44944. Finish. Okay, for the last question here, there is not that does not appear in the junior section. This is question number 11. Now, question number 11 here requires a formula that I believe none of you might know because it's not expected for you to know. If you have studied maybe secondary school math or Olympiad, then yes, you will know this formula. But otherwise, I don't see why you will go and purposely learn this formula beforehand. So the formula is this: a cube plus b cube plus c cube minus 3abc is equals to a plus b plus c times a squared plus b squared plus c squared minus ab minus bc minus ca. This is quite a well-known formula if you're doing secondary school math Olympiad, but definitely for primary school math Olympiad, it's not well-known at all. Now, using this idea, what you can think of for this question is that we can think of this question as a cube plus b cube plus negative 1 cubed minus 3 times a times b times negative 1. What is this going to be? If you take a look at what the question is doing, if you move the 1 over to the left, this is exactly the expression that you can get. So actually, if you move the 1 over to the left, this expression will be equals to 0. Which means that 0 is equals to a plus b minus 1 times this bunch. Now, this bunch actually, you can rewrite it in another way. You can rewrite it as half of a minus b squared plus b minus c squared plus c minus a squared. So in this case, it's going to be half of a minus b squared plus a minus 1 squared plus b minus 1 squared. Okay, let's deal with the easier case first. Let's deal with the case where the second term is 0. Okay. Okay, wait. Let me look at the two cases. So case 1, this is the one you look at. Case 2, this is the one you look at. Okay, so let's deal with case 2 first. Case 2 is 0, right? What are the possibilities here? Actually, it's just going to be a equals b equals 1. The reason is because you're adding up some square numbers. And square numbers you know must be at least 0, right? So if you know that square numbers are at least 0, then if you add up 3 numbers that are at least 0, turns out the answer is 0, what does it mean? It means that each of them must be 0, right? It means that a equals b equals 1 since a minus b equals to 0, a minus 1 equals 0, and b minus 1 equals 0. So this is one pair of answer. The pair is 1, 1. Okay? So the pair is pair 1, 1. There's only one number in this case, or rather one pair in this case. So this is the easier case. Now let's deal with the slightly more challenging one, which is the first expression is equals to 0. So what that means is that um, a plus b is equals to 1. How many possibilities are there here? If a plus b is equals to 1, we can go and list them out. A starts from negative 7 and b starts from 8, right? Because the lowest value of a is negative 7. So negative 7, 8, negative 6, 7, negative 5, 6, right? Dot, 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 until the first one increases to 8, the second one decreases all the way to negative 7. So these are the possibilities. Now, how many of them are there? There are 8 minus negative 7 plus 1, I believe. There are 16 pairs over here. Okay? So case 2 being 0, there's one pair. Case 1 being 0, there are 16 pairs. The final answer for this question is 17. 17 pairs of A and B that satisfy the given equation. Okay, that's it. Any questions? If nothing, then I'll stop here. All right. Yeah. Hopefully you found this RMO ground 2 papers interesting. I find them actually a little bit more interesting than your usual primary school math and questions. Okay, I'll stop here.